My name is Daniel, and today I'd like to give you some technical insight into how I got the display driver for the PICO 2 RP2350 edition working in a way that it can rotate and scale the display with almost zero CPU interaction. So, let's have a look, shall we? In a perfect world, the frame buffer in memory needs to be scanned out to the display just the way it has been placed in memory. However, in real life it might occur that this is not the case. For example, if you want to use a display that is mounted and being rotated by 90 degrees, the picture might even need to be scaled. In my case, for the PICO 2, I had to mount the LCD rotated by an angle of 90 degrees because it made the super thin bezels possible. In upright position, the LCD's controller IC would have been in the way. Also, I wanted to use a 720 by 720 display and upscale the image to fit the display. This gives you the super crisp pixel art experience that I was looking for. However, a single frame buffer would have been 1 megabyte in size. You could always have the CPU rotate and scale the frame buffer, but that cuts deep into performance and memory footprint. Luckily, the RP2350's DMA, in conjunction with the PIO, can do it. It's a little bit complicated, so make yourself comfortable. So, instead of sending a column's pixel data directly to the scanout state machine, the idea is to have a lookup table that contains the addresses to all the pixels in one column. Sending these values to the address register of a DMA channel will make the DMA fetch the data from RAM and send it to a PIO, which can then scan out the data to the screen. The PIO can scan out every pixel multiple times, say 3 times, effectively scaling the pixels in one direction. But it cannot scan out a line multiple times. The idea is that the lookup table as well contains the line 3 consecutive times in this example. If you choose the alignment properly and the length as a power of 2, then the DMA can mask the address and effectively scan out that very same lookup table again and again, since reading will wrap around after reaching the end of the buffer. There usually is a difference between the buffer length and the pixels that need to be scanned out. These quote-unquote superfluous pixels are being used for display syncing signals. You can see them here as blue arrows. This makes it possible to scan out the line scaled by a factor of, say, 3 in this example. However, you don't want to scan out the same line over and over again. So what needs to be done is to change the addresses in the lookup table by the amount of 2 bytes every time a line has been scanned out. The CPU could do it, but that would cause a massive interrupt storm. So, before pushing the data to the scanout state machine, we reroute it to another state machine, which only has the task to change the addresses. The PIO cannot increment it, but it can decrement it. So, this state machine will decrement the addresses, effectively shifting the column by 1 pixel. I also added an index column mode where you can have an 8-bit paletted frame buffer, and the PIO in conjunction with the DMA does the palette lookup for you. Credit here goes to Zulu SCSI on GitHub, who used the very same idea for an SCSI driver. Link is in the description below. And here's the data flow between memory, DMAs, and PIOs. First, the CPU will start DMA 0. DMA 0 will then send the lookup table to the read address trigger register of DMA 1. DMA 1 will in turn send the actual image data to the state machine 1 in order to have the indexed color decoded. DMA 1 also chains DMA 4, which will forward the decoded color address from DMA 4 to DMA 5's read address trigger register. DMA 5 will then send the actual color data to the second state machine, which will scan out the pixel data to the screen. DMA 4 will also chain DMA 2, and DMA 2 will then send the lookup table addresses to the state machine 3, which will decrement it and have DMA 3 update the frame buffer lookup table. After a whole frame has been scanned out, an ISR will reset the lookup table and re-trigger DMA 0. And here you can see it in action. This is a fast tile mapper that uses the interpolator to really speed things up. The track is made out of tiles. Here you can see 100 sprites all being rotated and scaled and are being drawn at 34 frames per second. That's the maximum frames per second you can get at 2x scaling due to PIO speed. This is 3x scaling. The driver supports double and triple buffering as well as variable frame rate, which comes in handy in case you don't have enough RAM for triple buffering. The driver definitely still is in a work in progress state, but on the other hand, it's definitely a proof of concept that like you can have the screen rotated and scaled with almost zero CPU intervention. Yeah, well, if you made it this far, then thanks for watching. I hope you enjoyed, and bye-bye.